In this lesson, we will introduce the topic of congruences. So in the 1700s and 1800s, when number theorists began proving deeper theorems about integers, they often studied properties of integers in arithmetic progressions. So recall, an arithmetic progression is a set of integers where a and b are fixed and k ranges over all positive integers or all integers, and we look at the set of all integers of this form. We've already proved that the arithmetic progression 4k plus 3 contains infinitely many primes. And we claimed that if a and b are both in the progression 4k plus 1, then a times b is also in this progression. So it was Carl Friedrich Gauss who invented the concept of congruences, and after analyzing arithmetic progressions, he noticed that oftentimes it was just the remainder of these expressions that was the key to proving these statements. So for example, every number in the arithmetic progression 4k plus 1 has remainder 1 when divided by 4. Every integer in the arithmetic progression 4k plus 3 would have a remainder 3 when divided by 4. So let's define congruences. So here's our definition. For integers a, b, and m, with m greater than 1, we say a is congruent to b modulo m, and often we'll just say mod m. So a is congruent to b mod m if m divides a minus b. So we see that congruence is actually a definition involving division. It's really a statement about indivisibility. So we expressed a is congruent to b modulo m as a, and it looks like an equal sign with 3 lines. So a is congruent to b, and then in parentheses you have to tell the modulus. So m is called the modulus. So a is congruent to b mod m. That's the way this is written. So this is the notation that Gauss presented in his work Disquisitiones Arithmetica in 1801. So a couple of notes about congruences. First, let's look at this as another way of talking about arithmetic progressions. So if we said that if m divides a minus b, right, that's the definition of a is congruent to b, then I can write a minus b as m times an integer okay. But if I rearrange this, I see that a equals mk plus b. So a is in the arithmetic progression mk plus b, where k ranges over all integers. So we see that saying that a is congruent to b mod m is the same as saying that a is in the arithmetic progression mk plus b. So this was actually a very, very important invention in studying properties of integers, and so we'll use this extensively in future lessons. I mentioned this earlier, but the number m is called the modulus. Okay, and I'm going to assume that the modulus m is greater than 1. You could assume that m is just an integer other than 0, because if a number is divisible by positive m, then it's also divisible by negative m. So it's just usually easier to think of the modulus as always a positive number. If m equals 1, saying that something is divisible by 1 isn't very helpful. So we're going to assume that the modulus is always bigger than 1, an integer bigger than 1. And as we see from the definition of congruence, that congruence is really just a statement about divisibility. If I said that a is congruent to b mod m, then that's the same as saying that a and b would have the same remainder when divided by m. So a and b have the same remainder when divided by m. So let's look at some quick examples of congruences. Nine is congruent to 1 mod 4. Because, by definition, 4 divides 9 minus 1, which equals 8. So 9 is 1 more than a multiple of 4. 20 is congruent to 4 mod 8. You can think of this as 20 is 4 more than a multiple of 8, or by definition, using the definition of congruence, 8 divides 20 minus 4, which is 16. 17 is congruent to negative 4 mod 3. Why? Because 3 will divide 17 minus negative 4, which is 21. Ten is congruent to, well, let me leave it blank for a second. What is 10 congruent to mod 5? Well, 10 is a multiple of 5. So 10 will be congruent to 0 mod 5, because 5 divides 10 minus 0, which is 10. We can also say that something is not congruent to by putting a slash to the congruence symbol. So, for example, 8 is not congruent to 3. That's how you would read this, mod 2. So 8 is a multiple of 2, so 8 would be congruent to 0 mod 2. And we see that by definition, 2 does not divide 8 minus 3, which is 5. So there's a few examples of congruences. And now I'm going to prove that the relation congruence is an equivalence relation. So let's look at some properties of congruences. So we will assume that A, B, C, and M are integers, and again M is going to be our modulus, so M is going to be greater than 1. Then it's true that congruences, the congruence relation is reflexive. That is, that every integer is congruent to itself, mod M. So A is congruent to A, mod M. Congruences also are symmetric. So if A is congruent to B, mod M, then B is congruent to A. Mod M. Third, congruences are transitive. Which states that if A is congruent to B, mod M, and B is congruent to C, then A is congruent to C, mod M. So these three properties of congruences make this relation an equivalence relation. So the relation is congruent to is an equivalence relation. So let's prove these three properties. So for 1, A is congruent to A mod M if and only if M divides A minus A, which equals 0. And clearly any integer M will divide 0. 2. Suppose that A is congruent to B mod M. So if A is congruent to B mod M, and by definition M divides A minus B, then I can write A minus B as an integer multiple of M. So A minus B equals MK for some integer K. But then just multiplying both sides by -1, I see that b minus a is equal to m times negative k, where k is an integer. Therefore, m divides b minus a, and that is the definition of b congruent to a. Okay. So for part 3, assume that a is congruent to b and b is congruent to c mod m. So a is congruent to b and b is congruent to c mod m. Then by definition, m divides a minus b and m divides b minus c. So m is a common divisor of a minus b and b minus c, so it will divide any linear combination of a minus b and b minus c. In particular, m divides the quantity a minus b plus b minus c. This equals a minus c. Therefore, m divides a minus c, and that's the definition of a being congruent to c mod m. So we've just proven that the congruence relation is an equivalence relation. I want to give one more property that can be kind of useful to think of. For when is a congruent to 0 mod m? I showed an example earlier that 10 was congruent to 0 mod 5 because 10 was a multiple of 5. So a is congruent to 0 mod m if and only if m divides a. And this is a very simple property to prove. By the definition of congruence, if a is congruent to 0 mod m, then m divides a minus 0, but that is a. So now we will prove some algebraic properties of congruences. So let a, b, c, d, and m be integers with m greater than 1. Then if a is congruent to b mod m and c is congruent to d mod m, then a plus or minus c is congruent to b plus or minus d mod m, and a times c is congruent to b times d mod m. So after we prove this theorem, this will justify using the usual operations of addition, subtraction, and multiplication with congruences having the same modulus. So let's prove this statement. Okay, so we're assuming that a is congruent to b and c is congruent to d. So a is congruent to b and C is congruent to D mod M. Therefore, M divides A minus B, and M divides C minus D. Then we can write A minus B as an integer times M, so MK, and C minus D can be written as an integer times M, so let's write it as ML for some integers K and L. Okay. Now let's look at the sum MK plus ML. Then MK plus ML will equal A minus B plus C minus D. And if I factor out an M from both terms on the left, M times K plus L equals, let me rearrange the terms. So I have a positive A and a positive C, so A plus C. And I have a negative B and negative D, so if I factor out a negative sign, I can write this as A plus C minus the quantity B plus D. And we see that M times an integer equals A plus C minus B plus D. Therefore, M divides the quantity A plus C minus B plus D. Therefore, A plus C is congruent to B plus D mod M. Now I'm going to show that A minus C is congruent to B minus D, so we can replace C and D with negative C and negative D to obtain the required expression. So replace C and D with negative C and negative D above, which are still integers, to obtain A minus C is congruent to B minus D mod M. And the last statement we want to prove is that A times C is congruent to B times D mod M. Now A, which I can rearrange the expression above to give me A equals MK plus B, and C I can rewrite as ML plus D, and therefore when I multiply A times C, we see that A times C will equal MK plus B times ML plus D. When I expand this, I'm going to have a term B times D plus a bunch of terms with a factor of M. So I have an M squared KL, I have plus MKD, and plus MBL. So if I subtract BD from both sides of this expression, I see that AC minus BD can be written as M times the quantity MKL plus KD plus BL. Therefore, M divides AC minus BD. And we can conclude that AC is congruent to BD mod M. So this theorem says we can do the usual operations of addition, subtraction, and multiplication with congruences. So this theorem says we can do the usual algebraic operations addition, subtraction, and multiplication with congruences having the same modulus. But we have to be a little bit more careful with divisions. We'll wait for a few minutes before we talk about dividing with a congruence. But first, let's look at some examples. So for example, if we wanted to solve a congruence, such as x plus 3 is congruent to 7 mod 10, so we could look for a single integer that would solve this, and a single value for x that you could plug in to solve this congruence. But there's actually going to be an infinite number of integers that satisfy this congruence. So we want to kind of classify all the integers that satisfy this by getting x by itself on one side of the congruence. So we see that if x plus 3 is congruent to 7, then I can subtract 3 from both sides of this congruence. And we see that x will be congruent to 4 mod 10. So any integer that is 4 more than a multiple of 10 will satisfy the original congruence. So this is the solution to this congruence. So any integer that is congruent to 4 mod 10 will satisfy the original congruence. In the next example, 117 is congruent to 5 mod 7. So you can think about it as, you can think of this statement as 117 is 5 more than a multiple of 7. Number 212 is congruent to 2 mod 7. So look at this expression. What is 117 times 212 congruent to mod 7? Well, instead of multiplying these two larger numbers together, we can just say this is congruent to 5 times 2 mod 7, which is 10. But 10, I can write 10 as 3 mod 7. If I subtract 7 from 10. So we'll talk about this more in the next lesson, but often we write the answer as a number between 0 and 7 if 7 was the modulus. So for example, if you had a modulus m, you often write the solution to a congruence as a number between 0, 1, 2, up to m minus 1, mod m. Here's another example. So suppose 25x is congruent to 3 mod 4. So let's solve this congruence. So we want to get x by itself. So we can add or subtract multiples of the modulus to either side of this congruence. So if I want to get x by itself, I need to get rid of this coefficient of 25. So one thing we could do is we could subtract 4x from this side, or any multiple of 4 from 25x. So I'm going to subtract 4x from the left-hand side, and from the right-hand side, I'm just going to leave it alone because negative 4x is congruent to 0 mod 4, because negative 4x is a multiple of 4. So I can reduce 25x to 21x, and I'm going to continue this process. So 21x is congruent to 3. If I keep reducing by 4, I see that 21x is congruent to 17x. If I subtract 4x, this is congruent to 13x, which is congruent to 9x, which is congruent to 5x, which is congruent to 1x, or just x. And we said that 21x was congruent to 3 mod 4, so therefore x is congruent to 3 mod 4. From the original congruence, 25x is congruent to 3 mod 4 will be satisfied by any integer that is congruent to 3 mod 4. Now let's talk about dividing. Look at this expression. If this was an equation, you might divide both sides by 25, but we can't write 3 divided by 25 in congruences because we always have to have integers in our expressions. So let's talk about division with another example. So in this example, I want to solve 2x is congruent to 6 mod 8. Okay, so we see that 6 is divisible by 2, so we would like to divide by 2 to obtain x congruent to 3 mod 8. So we'd like to divide by 2 to obtain x congruent to 3 mod 8. So it looks like x is congruent to 3 mod 8 is a solution. And it is, but this is only part of the solution. Because consider x congruent to 7 mod 8. So if x is congruent to 7 mod 8, then x is also a solution to the original congruence. To see this, let's plug in 7 for x, so 2 times 7, which is 14, and that is congruent to, if I subtract 8, that is congruent to 6 mod 8. So we see that there seems to be 2 solutions. X is congruent to 3 mod 8 and x is congruent to 7 mod 8. So the problem with our division is that when we divide it by 2, notice that the modulus 8 is also divisible by 2. We have to worry about that when we're using division. So the problem is that we divided by 2, and 2 and 8 are not relatively prime. In other words, the greatest common divisor of 2 and 8 equals 2. So if you're divided by a number that's not relatively prime to the modulus, you have to change the modulus. Here's why. So if 2x is congruent to 6 mod 8, then by definition of congruent, 8 divides 2x minus 6. That means that 2x minus 6 is congruent to 8 times an integer k. But this equation, I can divide everything by 2 to obtain x minus 3 is equal to 4k. And this tells us that 4 divides x minus 3. And therefore, x is congruent to 3 mod 4. So in the original congruence, 2x is congruent to 6 mod 8. If you want to divide by 2 here, you actually would have had to divide the modulus by 2 as well. And we see that the full solution is any integer x that's congruent to 3 mod 4 will satisfy the original inequality. And we see that if x is congruent to 3 mod 8 or 7 mod 8, those are both solutions that are equivalent to x congruent to 3 mod 4. So let's define division in congruences more formally. Division in congruences theorem. If a, b, c, and m are integers with m greater than 1, and d is the greatest common divisor of c and m, and AC is congruent to BC mod m, then A is congruent to B. So if I cancel or divide both sides by C, then A is congruent to B, but I have to change the modulus to M divided by D. So if we divide both sides of a congruence by a divisor of the modulus, then we'll have to divide the modulus as well. So let's look at the proof. If AC is congruent to BC mod M, then M divides the quantity AC minus BC, which equals C times A minus B. So I can write C times A minus B as M times some integer K and now I can divide both sides of this equation by the greatest common divisor of C and M, which is D. So I'm going to divide both sides of this equation by D, and this implies that C over D, which is an integer, times A minus B equals M over D times K. So look at this expression. M over D and C over D are now relatively prime because I've divided them both by the greatest common divisor. Okay, so we're going to use this fact. So since the greatest common divisor of M over D and c over d is 1. Okay, so these m over d and c over d are now relatively prime. This expression shows that m over d divides c over d times a minus b. But m over d is relatively prime to c over d, then by Euclid's lemma, m over d must divide the other factor, a minus b. So since the GCD of m over d and c over d is 1, m divided by d must divide a minus b. By Euclid's lemma. If you recall, Euclid's lemma said that if an integer divides a product and is relatively prime to one of the factors, it must divide the other factor. But if m over d divides a minus b, then that's equivalent to saying that a is congruent to b mod m over d. So I'm going to give a quick corollary of this theorem. Which I'm going to call the cancellation rule. So by the previous theorem, we can conclude that if AC is congruent to BC mod M, and C is relatively prime to M, so the GCD of C and M is 1, then we can cancel the C from both sides. In other words, we can divide both sides by C without changing the modulus. Then A is congruent to B mod M. So this is just a quick corollary from the previous theorem because we're assuming that the greatest common divisor was 1. So then m divided by 1 is still m. So if you have a congruence with a common factor on both sides of the congruence and the common factor is relatively prime to the modulus, then we can cancel that common factor. So let's use this theorem and this corollary, the cancellation rule, to solve some congruences. Let's solve the congruence. 5x is congruent to 4 mod 3. So right now 5 and 4 have no factors in common, but I can subtract 3x from the left hand side because 3x is congruent to 0 mod 3. So we see that 2x is congruent to 4 mod 3. Now I have a common factor of 2. 2x and 4 are both divisible by 2, and since 2 is relatively prime to 3, so since the GCD of 2 and 3 equals 1, we can cancel this common factor of 2 and write x is congruent to 2 mod 3 when I divide both sides by 2. Let's solve another congruence. So now let's solve 5x plus 7 is congruent to 11 mod 3. Well, let me subtract 7 from both sides. So I get that 5x is congruent to 4 mod 3. And again, we can't divide by 5 yet, but I can add multiples of 3 to the right-hand side. So I see that 5x is congruent to 4, which is congruent to 7, which is congruent to 10 mod 3. So in the expression 5x is congruent to 10 mod 3, I can now divide both sides by 5, or cancel a common factor of 5, to get x is congruent to 2 mod 3. Again, I can do this because the greatest common divisor of 5 and 3 is 1. So we can cancel a common factor that's relatively prime to the modulus without changing the modulus. So x is congruent to 2 mod 3. So any number that's 2 more than a multiple of 3 will solve the original congruence. Let's look at one more example. Solve 3x is congruent to 23 mod 77. So I'd like to divide both sides of this congruence by 3, but 23 is not a multiple of 3. So I can add 77 to the right-hand side to obtain 3x is congruent to 100. And that's still not a multiple of 3, so I'm going to add 77 again. So 3x is congruent to 177 mod 77. And 177 is a multiple of 3. If you notice, if you add the integers 7 plus 7 plus 1, you get 15, which is a multiple of 3. So we can tell that it's divisible by 3. So now I'm going to cancel a common factor of 3, and I see that x is congruent to 59 mod 7. So here again, I could cancel a common factor of 3 because 3 is relatively prime to 77. So there's one way to solve this congruence. Let me show you an equivalent way. So we don't often think in negative numbers, but if I start out with 3x congruent to 23 mod 77, if I actually subtract 77, I'll get a multiple of 3. 3x is congruent to negative 54 when I subtract 77. And 54, negative 54 is divisible by 3. So when I cancel a common factor of 3, I get that x is congruent to negative 18 mod 77. And negative 18 is congruent to 59 mod 77. So again, we often write our solutions to congruences as a number between 0 and 1 less than the modulus. So I want to add 77 to get that x is congruent to 59 mod 77. So either one of these are solutions. I just wanted to show you another solution where we're involving negative integers.